to kick off the SambaNova training with an introduction to our DataScale SN30 product, which is deployed in the ALCF testbed, as Varuni mentioned. Just a quick safe harbor statement. Today, what we will cover are a few things. We'll go through our core technology stack. I'll talk about the SN30 details, how this looks like in large deployments like the ALCF has, and then I'll share a few other announcements that we have from SambaNova that you can explore on the web with us. So since I wasn't sure of the audience, I thought I would start with a quick introduction to SambaNova Systems. We were founded as a company back in 2017, but before that, we were grounded in research with one of our founders, Kunle Olakoden, who's a professor at Stanford University with research funds from DARPA. So this effort has been over a decade in the making. We've been shipping product now for almost 4 years, and the SN30 is our third generation product that is deployed in the ALCF. We build a full stack solution from chip to models to orchestration for enterprises, research institutions like Argonne, and public sector agencies worldwide. We have lots of investors that have been helping us on this journey, and we're excited to be part of the testbed here at Argonne. So I usually like to start off with a what does SambaNova build? And as I mentioned, we are a full stack AI hardware provider, and we actually express that in 2 different products. I'll mention both products simply so you understand what SambaNova offers, but please note that what is deployed to date in ALCF is our DataScale product. So as I mentioned, we build chips, which we call reconfigurable data flow units, and I'll dive into those details in a little bit. We package those into systems and deliver software that we call SambaFlow. And then this is then packaged and delivered in our DataScale platform. The software that's in SambaFlow will be detailed a little bit later today, but it's essentially a compile and runtime stack. Users interface with our DataScale product through a common ML framework like PyTorch, and then they can bring their models to our platform to iterate on them and get efficiencies and key capabilities that we offer. Our SambaNova Suite platform, I'll just mention, basically takes our DataScale platform, packages it as a service. Customers get pre-trained models that they can then fine-tune and infer on. They can also train from scratch if they're interested in that. SambaNova Suite, while a great product, is not what is deployed at ALCF, so we'll focus mainly on DataScale through the course of this training. When we started the company, and even when we were grounded in research out of Stanford University, SambaNova had a few thoughts on what really would enable these types of AI workloads. And the good news is what we grounded in research over a decade ago and put into a company back in 2017 are really the same key enablers now that they were back then. And so generative AI and AI models, these large ones, whether they're large language models, multimodal, recommendation, large vision models, they all really need 3 things. So the first is compute. Compute is now basically a commodity and is universally provided by a lot of vendors. The other 2 things, however, that are extremely important and need to be done in tandem are 2 things. The first is memory capacity. This is a huge pain point on a lot of traditional architectures. And so how do you get large memory capacity where you can fit these large parameter models that have very long sequence lengths or very large vision models in memory so that you can access them and handle them quickly? At the same time, having memory capacity that's quite large is not enough. You really need to combine this with what we call data flow, which basically is how your data moves through the system and how you can merge things together for the most efficiency. And so what we bring to the table from SambaNova is a compute platform that has very large memory capacity and multiple tiers of memory capacity, combined with the data flow architecture to really drive efficiency and innovations that other platforms aren't able to do. And so if this is basically a cartoon example where I can talk people through what is data flow and how does that combine with our large memory to really be the most effective implementation for generative AI and other AI workloads. So if you look at a very simple convolutional graph here that we have on the top, you can think about how you might deploy that on a traditional CPU or GPU. Essentially, the kernels will be loaded kernel by kernel, and you'll grab, when you start, batches and weights from memory. In an NVIDIA GPU environment, this will be high bandwidth memory. You'll bring that over to the core where you have your first kernel. You'll execute. The results will go back to memory. You'll do a context switch, load the next kernel, and bring the data and weights back. And so what happens in this kernel by kernel approach is that there's a lot of context switching, which is overhead, and there's a lot of back and forth to memory. And so technologies like high bandwidth memory are required, and then you're limited by the capacity that that technology offers. So what we've done at SambaNova is combine a few things. We've taken large DDR memory and put it very close to our chip. And we've combined that with our reconfigurable data flow unit that has intelligence PCUs and PMUs with very high amounts of SRAM on the chip, where we can spatially lay out different nodes in the network and then stream data from DDR memory through the chip and through many nodes in the graph to basically get the most effective implementation where we eliminate memory traffic and the context switching that you see on other platforms. So with that, I'll just give you a few details about our 3rd generation chip, which is the SambaNova Cardinal SN30 RDU. Once again, an RDU stands for Reconfigurable Data Flow Unit. This generation of technology was built at TSMC using their 7-nanometer technology. It was our 3rd generation at this technology. We essentially, in this generation that's in the ALCF testbed, I mentioned that we have multiple tiers of memory, and there's 2 tiers of memory on this chip. You have SRAM, which is on chip, and that's 640 megabytes. And then you have access to very large GDR, so a terabyte per chip. And then if you look at the total teraflops, that's what we provide in bfloat 16, which is our main workhorse. Oh, sorry, I went the wrong direction. If you look inside the chip, an RDU is essentially broken into 8 individual tiles. Each tile has what we call pattern memory units and pattern compute units. If you can think about that, the compute unit is where we do all of our compute processing, and the memory units are really intelligent memory structures, and that's how the memory is broken up on the chip as SRAM. We essentially connect all of the PMUs and PCUs with a switching fabric and route and optimize how data flows through the system in the most intelligent and effective way. When we deploy these systems, models, whether it's for inference, fine-tuning, or training, can use a variety of configurations. Multi-tenancy is built in from the bottom up. When you have these RDUs, regardless of what tile you are on, you have direct access to DRAM across the entire system. And then you also have the ability to scale out to other systems through our PCIe connected fabric. And so if you just zoom in on one of the tiles, you'll see this cartoon representation of what the internals of our chip looks like. And I've sort of mentioned at a high level our pattern memory units and our pattern compute units. In addition, we have a switching fabric with the nodes in the switching network denoted by S. Address generation unit and coalescing units are essentially how you're going to get out to DDR. Now, the good news about our technology is that individual data scientists and engineers who are using our system don't need to understand all of the details of our chip and really get to under the covers what all these things are doing and how to optimize them. Our software stack handles that for end users. And so this is really just for informational purposes. So that is a great time to just quickly talk about the software stack. We do have a section later today that will go into this in detail. But across our two products, we provide different entry points for end users to interact with our stack. Here at Argonne, on the ALCF testbed, where we have our DataScale systems, we really expect most of the researchers who are using our systems to be ML engineers. And basically what that means to us is they will be authoring their own models or using open source standard models that are provided for easy consumption. But they are people that will iterate on models, work on performance tuning, and deploy them. And so they will be interacting with our DataScale system and our SambaFlow software stack through the interfaces that we provide. I did mention a little bit about multi-tenancy and concurrency. Our platform has been built with these things in mind since the first generation. And so you can imagine within a system and then across systems, ALCF has 8 nodes. You can run a variety of workloads, either multiple users, multiple application, or a single user, a single application, or many users, many applications. So all of that has built in from our very first day, and we continue to evolve on that in our product. So we essentially package our chips into systems that we then package into what we call DataScale racks. And these DataScale racks at ALCF are our DataScale SN30 generation. And so they are optimized with our systems built inside, and they also have things like power and networking to make sure that they're optimized and integrated. A single system is actually 10 RU, and what it includes is 8 of our reconfigurable data flow units, a total of 8 terabytes memory across those 8 RDUs. All of the memory is accessible. There's certainly some NVMe and other disk space, and there's an x86 host module, and everything is connected by PCIe Generation 4 technology. Within a rack, we actually at Argonne have 2 of these nodes deployed per rack if you're interested in the physical information. And so there's a multi-rack deployment in the ALCF data center. So with that, I know we have just a few more minutes to go through. I wanted to talk about a few exciting announcements that SambaNova has made recently, and you may have seen details on externally. I should mention that all of this is based on our latest generation technology, which is an SN40. This is not available in the ALCF testbed today. But what I can say is much of what I'll talk about is available to anyone worldwide to try and explore online for free. And so I encourage folks to get an understanding of what we have new to offer, especially in the world of generative AI inference. So our SN30 platform in Argonne is a platform that can do both training and inference, and we'll cover that throughout the training over the next couple of days. The inference on the SN30 platform really shines for greater than batch size 1 training. And so our SN40 platform is really where generative AI inference has been optimized, and I'll explain why in a minute. But one of the things that we've recently announced is something called SambaOne, which is a composition of expert model that we've released. It's a 1.3 trillion parameter model that is a mixture of smaller models. Within this composition, we have a variety of model architectures from Llama to Mistral to Falcon to Lava, dplot, Clip, etc. And we deliver it as over 50 experts. It covers a variety of tasks and domains and languages. And customers can leverage this all in a single interface and a single endpoint. So if you'd like to see what this looks like on our latest generation platform, and you'd like to understand how these composition of expert models performs from SambaNova and on our SambaNova platform, you can try it at the link provided below. We're always innovating there. And I think right now we're basically showing any of these models operating at over 400 tokens per second. And this is essentially a single system. So one 8-socket machine can run a model the size of 1.3 trillion parameters and achieve high levels of concurrency for numerous users. And everybody likes to see, well, great, you have a model, but actually, how does it perform? And so certainly this information is subject to change as models move forward. But the latest information that we have is that compared to very common models, very large models that people use, GPT 3.5 Turbo and GPT-4 as examples, SambaOne matches or surpasses all of these closed source models. And so we suggest that you go and try what SambaOne has to offer. If you look at our website, you can also see we've compared it to other very large models that are out there, and we see similar results. People often ask us, how does this composition of experts work? And so I'll just do a quick introduction here if you guys decide to play with composition of experts externally on our SN40 machines. Essentially, when we deliver a composition, as we have in SambaOne, it's roughly 50 plus models. There is a model that sits at the top to do expert routing. This is today sort of an LLM that does simple classification, and it will route to the necessary expert that's included in SambaOne. So for a research community, you can imagine you have a composition of experts that have different experts, maybe in chemistry, biology, materials development, etc. And the user would put a prompt directly to the one endpoint. The expert would then say, this is a biology expert, or I need to route this to the chemistry expert. And we can quickly go through these expert models, load the appropriate one, and run at these very fast token counts that you can see in the demonstration link that I provided. And the benefit of the SN40 is we have 3 tiered memory. We have SRAM and large DDR like we do on the SN30 at ALCF, but we also have introduced high bandwidth memory. And so we are able to store all of these experts in large DDR memory and access them instantly, the ones that need to be called up through the high bandwidth memory. And so just closing it out, the SN40 is not yet an ALCF, but this is what you can use when you go to some of the things you've seen on our website, whether it's our fast token count or some of the other things I'll talk about in a minute. Everything behind those publicly available things to try is based on our SN40 technology. And the main difference here is that it's a 5 nanometer technology, and we've added an additional tier of memory, mainly the high bandwidth memory, which really helps with generative AI inference, especially batch size 1. And so 2 other things you may want to try that are publicly available. We have something called Sambaverse, and we can make sure that we get the links for you guys, or you could just put it into Google and it will come up. Essentially, it gives the power of SambaOne to any developer. You can use this to try out different models and your prompts, right? So it may not be your full benchmark set that you want to do, but if you just want to understand how different models with different prompts perform, you can compare 6 models at a time currently, and all of this is coming from our SambaOne model platform running on SN40. The other thing that we have is we have things called Samba apps, and this is ways for end users to experience the power of SambaOne through some sample applications. So Samba Chat is one of them, and the latest link to Samba Chat was in the few slides before. Here you can basically ask a variety of experts questions and see how the routing methodology works. We also have some document examples. Now, these look very much for enterprise, but you can imagine that these very simple examples could be used for research documents or other things. And so with that, I think that is the end of the hardware presentation.